Well, you clicked on this video and you probably read the thumbnail and maybe you're thinking, is he mad saying that the 555 is not a timer? Of course it's a timer. Well, actually, in my view, it's not a timer at all. And when I first discovered the 555 as a kid, I thought, great, there's a chip that I can really use. It's going to do my timing stuff for me. And I was actually a little bit disappointed. So here's what I mean. This is the circuit diagram for a 555. It was designed in 1971, so it's very old, long established chip and still very, very popular. But inside here, you've got transistors, you've got diodes, and you've got resistors. There's absolutely nothing in here that gives you any form of time base. But that's not really what this video is about. I wanted to go through how a 555 timer works and how you actually make it into a timer with the components you put around it. So let's take a look. So here's the 555. It's an 8-pin device. Pin 1 is ground and pin 8 is your voltage supply. Now between pins 1 and 8 there are 3 5k resistors. Some people say that's where the 555 got its name from, and I think that's probably absolutely right, but some people say not for some strange reason, I don't know why. Anyway, they are wired in series like that. So 3 5k resistors in series, well that's 15k resistance, you just add them together. Now if you look at the points along this circuit here now, then over here obviously that's going to be 0 volts because it's wired to ground. But at this point, this is a voltage divider, so you work out 5 over the total 15, you're going to get 1/3 of your supply voltage at this point. And at this point, you're going to get 2/3 of your supply voltage at that point. And then here, of course, you're going to get your supply voltage because it's wired to it. So I'm going to make this 9 volts because it means that these come out as whole numbers. But actually, the datasheet tells you that you can go from anything from 4.5 to 16 volts that you can drive this 555 at. So at 9 volts, then these voltage dividers, this is going to be 3 volts at this point, and this will be 6 volts at that point. So let's just move that up there. And the next stage in the 555 are these. They are called comparators, Comparator 1 and Comparator 2. I'll explain what they do in a second if you're uncertain. But basically they are wired like this. So Comparator 1, the positive leg on that goes to your 1/3 supply, or 3 volts in our case. And the negative terminal goes to pin 2, which is called the trigger. On Comparator 2, the negative terminal of that goes to our 2/3 voltage reference there, which is 6 volts in our case. And the positive terminal goes to pin 6, which is called threshold. And let's just take a closer look at the comparator then. This is the symbol for a comparator. Now this plus and minus terminals here, that's not the supply. Supply is normally shown like that. And on this side, we've got an output, which we'll look at in a second. Now you can think of this as whatever's on this pin is compared with whatever comes in on this pin as a voltage. So this you can think of as your reference voltage, and you're just comparing whatever comes in here with this. So in our case, this pin is wired to our 1/3 voltage, or 3 volts. So if we wire up a variable voltage supply here, and we can start to crank up the voltage and see what happens. So when this is lower than my reference voltage, the output will be high. As we turn the voltage up, well, it's still lower, so the output remains high. Now at 2 volts, it's still lower, so the output remains high. We get to 3 volts, it's equal, it still remains high, but the moment you go over, then the output becomes low. And it doesn't matter how far up you go, it will then stay low. Okay, so that's a comparator. Now, pin 5 gives you an optional control voltage. So if you didn't want your 2/3 supply to be the control voltage on this negative terminal of comparator 2, you can feed in an external voltage here and it would use that instead. But the next stage off from these comparators is basically a flip-flop, and I'll discuss what a flip-flop does in a second. The output from comparator 1 goes to the set pin of the flip-flop, and the output of comparator 2 goes to the reset pin of the flip-flop. The inverted output of the flip-flop, so you've got Q is its normal output, But in the 555, we take the inverted output. This little line above the Q, that means not Q or inverted. It takes a not Q, but then that goes into a driver circuit, just so it can drive some current. But this little circle here indicates that that's also a not gate. So effectively what we're going to get on output 3 is the normal output from the flip-flop, because it's inverted here and then inverted again. So effectively what you get here is what would be called Q, or the output from the flip-flop. And this driver acts kind of a buffer from the flip-flop. The flip-flop can't drive much current. And with this driver, then the datasheet tells you it can source or sink up to 200 milliamps, which is more than enough for most of our digital circuits. So let's just take a closer look at this flip-flop then. It's got two inputs basically. One is called set and the other is called reset. And on the other side, it's got two outputs. The actual output is called Q, but you have this inverting output, or not Q, on this side. So whatever this is, this will be the opposite. Now basically, when the set pin is triggered or set high, then it will set Q to high and it will stay there. It's latched even when set drops back down to 0 volts. And it's only cleared when reset goes high. Okay, so let's just have a look at that. So let's assume that Q is already in a low state, so therefore not Q must be in a high state. So if we say that both of these were low, that would stay as it is. The output is low and not Q remains high. Then if set goes high, then Q will go high and therefore not Q must go low. And it will stay like that even when the set pin goes back to a low state again. Now when reset goes high, that will reset the flip-flop, the latch state of the flip-flop. So therefore the Q output goes to low and the inverse of that must therefore be high. And it'll remain like that even when the reset goes back to low again. So it's basically a latching device. Whenever you trigger the set pin, you'll get a high output. Whenever you then reset it, it will go to a low output. And not Q is just the inverse of that. And of course, we've got the set pin is wired to the output of comparator 1 that's shown there, and the reset pin is wired to the output of comparator 2 is shown there. Now, as well as being connected to this driver output here, the not Q pin is also wired to this NPN transistor, and that is wired to ground on the emitter leg, and the collector is wired to this discharge pin. So when this goes to a high state and this transistor turns on, it will pull this discharge pin to ground. And pin 4 is reset pin. That is wired in through a PNP transistor to the flip-flop. It's basically another reset on the flip-flop. You must keep this reset pin held high if you don't want this to reset the flip-flop. If you want it to reset, then obviously you'd pull it to ground. For the purpose of this video, I'm just going to tie that to high because I'm not interested in a separate reset. So that is a 555 chip in a nutshell. You've got your voltage divider here. They go into these two comparators, and the two comparators drive the flip-flop. And in addition to that, you've got the driver, so it can sink and source sufficient current. You've got a reset pin, which goes via this transistor, and you've got a discharge pin, which goes via this transistor, and that's it. So let's just do some experimenting with it now. Let's just move all this out the way a bit, and let's put our supply rail up here. Again, I'm going to use a 9 volt supply. And if I wire my supply like that, so pin 8 is to my 9 volts and pin 1 to ground. And of course, I've got to tie this reset pin to high to prevent this flip-flop from accidentally resetting. Now this is a PNP transistor as opposed to this one, which is a NPN. Now tip for that, NPN never points in. That little arrow there on an NPN never points in. PNP points in. This little arrow points in. So on this PNP, there can be no current flowing from the emitter to the base because they're both held high. Therefore, no current can flow from the base to the collector or vice versa. And then I'll just wire an LED to the output, and we'd put a current limiting resistor between the LED and the ground pin. I'll put a voltage source here, a variable voltage source, and if we connect that both into the trigger pin and the threshold pin, so that as we adjust this voltage, that is being applied to both here and here. So it's going into comparator 2 on the positive terminal and it'd be going into comparator 1 on the negative terminal. So now let's just have a look at that with a bit of colour coding to see what is pulled high and what is pulled low by these kind of red and blue colour coding. So there you go, it's all kind of colour coded using this chart. So red being the high voltage at 9 volts and blue being low or 0 volts, and then you've got all this gradient in between. So starting at the top, we've got our 35k resistors, we've got 1/3 voltage there, which is 3 volts, because we got 1/3 of 9 is 3. We got 6 volts there, which is our 2/3 of the supply. Again, 2/3 of 9 is 6. This transistor is turned off because not Q is low, so the base of this is low. This comparator is high because this 3 volts is higher than what's on its negative terminal, which is 0. And this comparator, its output is low because its negative terminal is higher than its positive terminal. Positive is coming from this supply, which is currently at 0 volts. So because this is high, then the flip-flop has been set. So Q would be high, not Q is low. So that's why this transistor's turned off. And because that's low, goes through this driver, it inverts it, that's therefore high, and the LED turns on. The reset pin, as I said, is tied to high, so this is high. There's no current flowing here because they're both high, so therefore there's no current flowing from the collector either. And basically what's going to happen with this circuit as we increase the voltage here is as per this table. So all the time this voltage is less than or equal to 3 volts, comparator 1 will stay high and comparator 2 will stay low. That's because comparator 1, we're comparing 3 volts with whatever comes in on this leg. So if that's less than or equal to 3 volts, it will stay high. It will only go low when the negative terminal exceeds whatever we have on here. On comparator 2, however, the voltage actually comes into the positive terminal, so our reference is constantly changing. So it's comparing a changing reference with this 6 volts. All the time that this is lower than 6 volts, and of course we are because we're down below 3, then the output will be low. And because this comparator 1 has gone to a high state, obviously it's triggered the set pin. So the set pin on the flip-flop is therefore set, and the not Q state would be low. If the voltage exceeds 3 volts but is less than 6, then the output on comparator 1 will then drop to low because the voltage on the negative terminal has now exceeded what its reference on the positive terminal. And on the comparator 2, nothing changes because we're actually comparing with 6 volts over here and we're down below 6 volts. On the flip-flop, no change. So even though this is dropped to low, the output has been latched. The set hasn't been reset and the reset hasn't been triggered either. So the output is latched as low. And when we get to a point that it's greater than or equal to 6 volts, then comparator 1 will stay low, but comparator 2 now goes high. That's because the voltage on this positive terminal now is above 6 volts, and this we're comparing with 6 volts, so therefore that would go high, and therefore it would trigger the reset and the flip-flop gets reset. So let's just have a look at that. So we're up at 1 volt now, as indicated by this needle, and the colour is slowly changing. The state has not changed at all. Everything, this is still high, this is still low, this is still low. This discharge pin is floating, by the way, because this transistor is turned off. So effectively, that's like a switch that's open there. So this input here is floating. And if we go up slightly more, so we're now at 2.5 volts, no change. Now, when we reach the threshold of 3 volts, of course, then we start to change the effect on this comparator. So comparator 1 now has gone to a low state. That's because the voltage on its negative terminal now exceeds its reference, which is at 3 volts. But nothing changed on the flip-flop because it's been latched. Okay, so until we get a reset signal, that's going to stay as a low output, meaning this goes to high, the LED is still on, the transistor is still off, so this is still floating. So let's now jump up, we're at 5 volts, no change, Now we're going to go at 6 volts or higher, and this comparator 2 now goes to a high state. That's because the voltage on this pin here on the positive terminal is now exceeding the voltage coming in on the negative terminal, so it's a high state. That means the high pin here, it triggers the reset on the flip-flop, so the flip-flop output is low. The inverted output, the not Q, which is the one we're using, therefore is high. And because that's high, it goes through this driver, inverts it so it's a low state, and therefore the LED turns off. Now, in addition, you'll notice that the not Q being high has turned this transistor on. The base has been pulled high. There's therefore current flowing from the base to the emitter, which means current can flow from the ground through to the emitter as well. So this pin here is now effectively connected to ground. So let's just go over to the bench now and see this in the real world. And there you go, there's the 555 chip in the breadboard there. I've got 9 volts coming in as my supply, and they go into pin 1 and 8 over here on the chip. Then I've taken the output through this resistor to this LED, and the other leg here is grounded. So when this is high, this LED comes on as it is now. This leg here is the reset pin, so that has to be held high to stop it constantly resetting. And this here is my separate supply coming in, which is this voltage. So I'm measuring it, and this is the voltage going to the threshold and the trigger pin. So I can adjust this, and you can watch it on there and see what happens. In addition, I've wired up this green LED to the discharge pin. So this is the discharge pin over here, through this resistor, onto that leg of the diode, and the other leg is actually on the positive rail. So when the discharge pin goes to ground through that transistor, then this LED will come on. So let's just turn this slowly up now, so you can see that the output is currently active, and we'll slowly increase the voltage. So it didn't go off when I went past 3 volts because it's a latch state. Now when I get to 6 volts, or roughly, there we go, the output has gone off and the discharge is now activated. So this discharge pin is now grounded, and therefore that LED comes on. So now if I drop the voltage, they go down, obviously below 6 volts now, but this is discharging, and that's still off because it's latched. And it won't be until I get down to 3 volts now that it changes state again. And there you go, the output's come back on and the discharge is now off. Okay, so what component can we put in place of this variable voltage source that will charge and discharge between these 3 and 6 volt thresholds over a period of time? And this is where this discharge will come into play. Well, of course, that's going to be a capacitor. So if we put a capacitor here and wire this leg to ground, then we're going to put 2 resistors here up to our 9 volt rail. Then we're going to wire the thresholds to the positive side of this capacitor, and also link that to the trigger as we did before. Therefore, the threshold and the trigger pin will be held to whatever voltage is on this plate of this capacitor. And then we wire our discharge pin to the middle of these 2 resistors. And as before, now let's just color code all this so we can see what's high and what's low and what's in between. So these 2 resistors act again like a voltage divider. This is at 9 volts, and the voltage slowly draws closer to ground as you get nearer to it. This capacitor is completely discharged at the moment, and therefore this voltage here is going to be somewhere in between this and this, depending on what the value of these resistors are. Let's assume that our LED is currently in an on state. Output from comparator 1 is high, output from comparator 2 is low. This is because we're back down at 0 volts again. So what's going to happen is this capacitor is going to start charging. It's going to go through these 2 resistors and start charging over a period of time. So now we're at 2.5 volts, nothing has changed. We're still below the 3 volt threshold, but the capacitor is still charging. As soon as we get to the 3 volt threshold, then the input voltage on the trigger pin coming to this negative terminal on comparator 1 suddenly exceeds the reference voltage, which is 3 volts. Therefore, this turns off. But nothing changes here because the output is latched. But once the capacitor reaches this 6 volt threshold, then 6 volts is coming into this positive terminal of this comparator. Therefore, we're now comparing with 6 volts. Given that we got 6 volts here from our 2/3 voltage divider here, then the output on comparator 2 goes high. Because it's high, the reset on the flip-flop is triggered. Therefore, the output of the flip-flop is low, the inverted output goes high, and the driver then turns that back to a low and the LED goes off. Also, because this is high, this transistor then turns on, meaning that this discharge pin is now pulled to ground through this transistor. And because it's pulled to ground, this now starts to discharge the capacitor through this leg. And also just to note that the 9 volt supply, of course, is also drawing current through that same discharge pin through this resistor. And what will happen now is this circuit will just keep on alternating between the upper and lower thresholds, turning the LED on and off, turning this transistor on and off, charging and discharging. So let's have a look at that on the breadboard. So there you go, back to the 555 on the breadboard. So you can see I've still got this red LED wired to the output. I've taken off the discharge one, we don't need to see that anymore. And I've got these resistor network boards here, they're great devices. And I've got the resistor 1 set to 10k at the minute and resistor 2 set to 100k. So it goes from the positive rail through a 10k, through 100k and then into my capacitor, and I've used a 2.2 microfarad there. Then this leg here from the positive side of the capacitor is going across here, and then that feeds the threshold and the trigger pin, and you can see the LED is flashing. So if I change the resistor values, then obviously the charge time or discharge time of the capacitor will change. So let's change this one from 10k to say, I don't know, 400. Let's go a big jump up. Sorry, that's 500. There you go. Look, you can see it's staying on a lot longer now. All right, let's put it back. And there you go. So there you go. That demonstrates how by just adding a capacitor and 2 resistors to the 555, you can configure it to be what's called an astable mode of operation. The output will alternate between a high and low state, and that's what was turning our LED on and off. Now, just have a look at the datasheet for the 555. There's many manufacturers, and this is just one datasheet. There's lots of manufacturers nowadays. This is the circuit, which is pretty similar to what I've shown you. It's almost identical. Difference being is they're just showing load resistors here rather than an LED. And they're also showing, well, actually you can have it so that it's either sinking current like this resistor would be. So one leg is at your VCC coming through here. Then when this goes to ground, then you'll have a current flowing through there. Or alternatively, as I have demonstrated, you can have your load grounded on this side, and then when this goes high, it will be live or current flowing through it. Now, one other thing they do as good practice recommend on your control voltage pin, pin 5, not to leave that floating because it's unstable. So you should really put a 0.01 microfarad capacitor on that leg. So just to show that on my version of the circuit, this capacitor here would basically go here across there to ground from your control voltage pin to ground. It'd be a 0.1 microfarad. But how did I get the timing right? How do you work this out? I had this as a 100k and this as a 10k resistor, and this is a 2.2 microfarad capacitor. So another extract from the datasheet then, here you go. The charge time is equal to, it works out to be 0.693 times your 2 resistors added together, this and this, times your capacitance in farads. And the discharge time, T2, is 0.693 times this resistor here, the second one, because you remember the capacitor is only discharging through that resistor, not both of them, multiplied by the capacitance in farads. So I had RA and RB, so RA is there, RB is there, and that's C there. So I had that as 100k, that as 10k, and the capacitor I had as a 2.2 microfarad. So if you work all that through then, the T1, the charge time, is 0.693, as it says there, times RA plus RBs, which is 110,000, times the capacitance. Now you've got to put it in, convert it into farads. So 2.2 microfarads is that in farads. And that works out to be 167 milliseconds. And the discharge time, T2, is 0.693 times this resistor, so RB, because it's only discharging through that resistor, which is 100,000, times our capacitance in farads, and that gives me 152 milliseconds. So let's go to the bench and just see what we got with an oscilloscope, and let's measure it. So back to the breadboard then, I've got my scope probe here on the output pin. I got rid of the LED, we don't need that anymore. So that's on the output pin of the 555, and I've just connected that into ground. One other thing I've changed is I got rid of this really cheap, dirty capacitor. I measured it and it wasn't 2.2 microfarad, it was way off of it. So I've used a different type in there and it was a bit more precise. And what I'm also going to do is to put a second probe on the positive side of that capacitor so we can see how it's behaving, the output behaves in relationship with the capacitor charge, okay? And you can see also, let's just click that on there, also I've got my 0.1 microfarad there on the control voltage. That's ground, that's going to pin 5 on there to make it more stable, all right? Let's have a look at the scope with this running then. So there you go, it's on the scope now. This is the output signal from the 555, so it's going high and low. This is set to 2 volts per division, so 2, 4, 6, 8, 9. It's halfway there, so that's my 9 volts going high and low state. Now, just to show you that 0.1 microfarad capacitor, the reason I added it before doing this is I'll just show you by taking it out on the breadboard right now, and you'll see what happens. Look at that, all that noise. So it does indeed have a impact on the stability of the output. So let's put it back now, and there you go, it's back in. Now let's just measure then, see what we actually get in terms of the on and the off time. Does it compare with our calculations? So if I just put my cursor on here, and let's measure on time first of all. So there. And it ends about there. Okay, and the delta we've got, don't know if you can see there, is 166 milliseconds. So what did we calculate? We calculated 167, so couldn't have got any closer than that. So that's good. Now let's measure the off time then. So over here, that's where it goes back up, and here, out there, and the delta on there is 152 milliseconds, and we calculate bang on. Wow, I didn't expect that. So that's bang on what we calculated. All good. Now let's just turn this cursor off then. Where's my cursor? It is there. Turn them off. Now let's put the blue trace on, which is the capacitor. So put him on there, and there you go, that's the capacitor. It's charging up from the 1/3 voltage there. That's when it triggers. Look, that's when it, let's look here. So it's charging up this point from 1/3 voltage. That's when it triggers to go the output high. Then once it reaches the 2/3, it triggers and drops the output low. There you go. So that's the capacitor alternating between the 1/3 and 2/3 voltage, and then it's obviously driving the 555 to turn its output on and off. Brilliant. So there you go, that worked out almost exactly. We had 166 milliseconds there, so almost, and we had exactly 152 milliseconds there, so the calculations do work. If you want to work out the frequency of that, then it's basically 1 over the on time plus the off time, and in this instance it works out to about 3 Hertz, okay? So that is the 555 timer, and it just proves that by adding a capacitor and a couple of resistors, then you can make it into a timer. It's the components that you put it around the device that make it a timer. Now I've only showed you the Astable operation, but there's a load of other operations, and I'll do some follow-up videos for some of those as well. If you found this video interesting and useful, then please click the like button. And if you haven't done so already, then please click subscribe too. All right, catch you later.